Level 1, solids. A solid is matter that keeps both its shape and its volume. The particles inside a solid are packed closely together, and strong forces prevent them from freely moving past one another. They are not completely motionless, however. Even in a solid object, atoms constantly vibrate around fixed positions. Heating the solid makes these vibrations stronger, while cooling it reduces them. Many solids have an organized crystal structure. Salt, ice, quartz, and most metals contain particles arranged in repeating geometric patterns. Other solids, such as glass and many plastics, are amorphous, meaning their particles do not form one clear repeating structure. The arrangement of these particles determines properties such as hardness, flexibility, transparency, and electrical conductivity. A steel beam and a rubber band are both solids, but their internal structures make them behave very differently. Under enough heat, pressure, or force, a solid can melt, bend, crack, or transform into another form of matter. Level 2, liquids. A liquid keeps a nearly constant volume, but it does not keep a fixed shape. Its particles remain close together as they are in a solid, but they have enough energy to slide past one another. This allows a liquid to flow and take the shape of its container. The particles near the surface of a liquid experience an effect called surface tension. Because they are pulled inward by neighboring particles, the surface behaves somewhat like a stretched elastic sheet. This is why water forms rounded droplets and why some small insects can stand on its surface. Liquids also have different levels of viscosity, which measures how strongly they resist flowing. Water has relatively low viscosity, while honey flows much more slowly. Most liquids are difficult to compress because their particles already have very little empty space between them. When a liquid is heated enough, its particles can escape and become a gas. When it is cooled, they lose energy and may lock into position as a solid. Level 3, gases. A gas has neither a fixed shape nor a fixed volume. Its particles are separated by large amounts of empty space and travel freely in different directions. Because of this, a gas expands until it fills every available part of its container. Gas particles constantly collide with one another and with nearby surfaces. These collisions create gas pressure. Increasing the temperature causes the particles to move faster, producing more energetic collisions. Reducing the available volume forces the particles into a smaller space, causing collisions to happen more frequently. This relationship between temperature, pressure, and volume explains everything from inflated balloons to weather systems. Unlike solids and liquids, gases can be compressed significantly. However, compressing a gas usually causes it to heat up. If a gas loses enough energy, its particles slow down and move closer together, eventually condensing into a liquid. The atmosphere around Earth is a mixture of gases, mainly nitrogen and oxygen, with smaller quantities of argon, carbon dioxide, water vapor, and several others. Level 4, plasma. Plasma is sometimes described as the fourth state of matter. It forms when a gas receives so much energy that electrons are separated from their atoms. Instead of containing only neutral particles, plasma contains free electrons and positively charged ions. Because these particles carry electrical charges, plasma behaves very differently from an ordinary gas. It can conduct electricity, generate magnetic fields, and respond strongly to existing electromagnetic fields. This can cause plasma to form glowing streams, loops, and filaments rather than simply spreading evenly through space. Plasma may seem exotic, but it is the most common visible form of matter in the universe. The sun and other stars are enormous spheres of plasma. Lightning briefly turns part of the atmosphere into plasma, while neon signs and fluorescent lamps use electrically energized gases to produce light. Plasma can also reach temperatures of millions of degrees, although temperature alone does not determine how dangerous it is. A very thin plasma may contain little total energy even when its individual particles are extremely energetic. Level 5, Bose-Einstein condensates. A Bose-Einstein condensate forms when certain atoms are cooled to temperatures extremely close to absolute zero, the lowest temperature physically possible. At this point, the atoms lose almost all of their ordinary thermal motion. Quantum mechanics says that particles can behave like waves. Under normal conditions, the quantum waves of separate atoms are too small and chaotic to notice. Inside a Bose-Einstein condensate, however, these waves spread out and overlap. A large collection of atoms begins behaving like a single quantum system, almost as though the individual particles have merged into one giant superatom. This state of matter was predicted by Satyendra Nath Bose and Albert Einstein in the 1920s, but it was not created experimentally until 1995. Bose-Einstein condensates allow scientists to observe quantum behavior on a scale much larger than an individual atom. They can be used to investigate extremely precise measurements, unusual forms of light, quantum computing concepts, and the fundamental rules that control particles at the smallest scales. Please consider subscribing if you're enjoying the video so far. I'll be uploading many interesting videos regarding physics, tech, and chemistry. Level 6 Superfluids. A superfluid is a liquid that can flow with almost no internal friction. In an ordinary liquid, particles collide and resist one another's movement, causing flowing water, oil, or honey to gradually slow down. A superfluid can continue moving for an extraordinarily long time without losing noticeable energy. Superfluidity usually appears at extremely low temperatures, where quantum effects begin controlling the behavior of the entire liquid. Liquid helium can become a superfluid when cooled to only a few degrees above absolute zero. In this state, it can pass through microscopic openings that would block an ordinary liquid. It can also climb the walls of a container and spread across its surface in an extremely thin layer. These effects do not mean that gravity or conservation of energy has stopped working. Instead, the particles in the superfluid are acting as one coordinated quantum system. Superfluid-like behavior may also exist inside neutron stars, where matter is compressed to densities far beyond anything naturally found on Earth. Level 7 Degenerate matter. Degenerate matter forms when matter is compressed so intensely that quantum mechanics becomes more important than ordinary chemical forces. It is mainly found inside the remains of dead stars. In a white dwarf, gravity pushes matter inward with enormous force. The electrons are squeezed together, but a quantum rule called the Pauli exclusion principle prevents identical electrons from all occupying the same state. This creates electron degeneracy pressure, which resists further compression and supports the star. If the star is massive enough, gravity can overcome this resistance. Electrons and protons are forced together, producing neutrons and forming a neutron star. The remaining matter is so dense that a small spoonful would have an enormous mass if it could somehow be brought to Earth safely. Neutron degeneracy pressure, along with interactions between nuclear particles, helps prevent the star from collapsing further. If the original star is even more massive, these forms of pressure may fail and the object can collapse into a black hole. Level 8 Quark-gluon plasma. Protons and neutrons appear to be basic particles, but each one is actually made of smaller particles called quarks. These quarks are normally held together by particles called gluons. The force between them is so strong that isolated quarks are not usually found under ordinary conditions. At temperatures of trillions of degrees, protons and neutrons can break apart. Their quarks and gluons are no longer confined inside separate particles, producing a state called quark-gluon plasma. This material probably filled the universe during the first tiny fraction of a second after the Big Bang, before the universe had cooled enough for protons and neutrons to form. Scientists recreate microscopic amounts of quark-gluon plasma by smashing heavy atomic nuclei together inside particle accelerators. Surprisingly, it behaves less like a chaotic gas and more like an almost perfect liquid, flowing with extremely low viscosity. Studying it helps physicists investigate the strong nuclear force and understand how the earliest matter in the universe developed. Level 9 Dark matter. Dark matter is the name given to an unknown form of matter that does not appear to emit, reflect, or absorb light. It cannot be observed directly with normal telescopes, but its gravitational effects can be measured. Galaxies rotate so quickly that the gravity from their visible stars and gas should not be enough to hold them together. Large groups of galaxies also bend light more strongly than their visible matter can explain. These observations suggest that galaxies are surrounded by massive, invisible structures called dark matter halos. Dark matter is estimated to make up most of the matter in the universe, but scientists still do not know exactly what it is made of. It may consist of particles that rarely interact with ordinary matter apart from through gravity. Many experiments are searching for these particles, but no confirmed direct detection has been made. Dark matter is also different from dark energy. Dark matter helps pull structures together through gravity, while dark energy is the name used for whatever is causing the expansion of the universe to accelerate. Level 10, antimatter. Antimatter is not simply matter with negative mass, nor is it an upgraded form of ordinary matter. Every known matter particle has a corresponding antiparticle with the same mass but opposite electrical charge and certain reversed quantum properties. The electron's antiparticle, for example, is the positively charged positron. When a particle meets its antiparticle, they can annihilate. Their mass is converted into other forms of energy, commonly producing high energy photons or additional particles. The reverse process can also happen. Enough concentrated energy can produce a particle and its antiparticle together. Small amounts of antimatter are created naturally by cosmic rays and some forms of radioactive decay. It is also produced in particle accelerators and used in medical technology such as positron emission tomography. However, antimatter is extremely difficult to store because it is destroyed as soon as it touches ordinary matter. One of the greatest unanswered questions in physics is why the observable universe contains far more matter than antimatter, even though the early universe appears to have produced both.